When it comes to the concepts of impulse and momentum, they're two slightly different but very, very related concepts. But they can tend to trip students up at first. So if we just take a look at the concepts behind these two, we'll take a look at the math later. The first thing to realize is that momentum, you may have heard this term before, maybe in a sporting event, like this team really has momentum going to the playoffs. And hopefully you realize that that means that that team is kind of on the move. They're going to be significantly harder to stop. They're gaining momentum, so to say. Momentum is actually extremely difficult to kind of define. It's a property that's very helpful that objects possess, and we can certainly use them to analyze motion very effectively, but it is kind of hard to actually define it. The best way that I've determined is kind of mass in motion. Um, Obviously, an object wants to keep doing what it's doing because of its inertia, but the momentum of an object just means that mass in motion, okay? And obviously, there's some parameters that will affect that. Now, if you think about this idea of the mass in motion is what momentum is, you'll find that momentum depends on two things. And if you think about this, it kind of makes sense. First of all, how much stuff is moving, that's the mass, right? How many particles, how many atoms are actually moving? Because the more atoms you have, the more momentum you have, just like the more players on a team or the more wins they have, you kind of, for that analogy, the more momentum they have. But also how fast that stuff is moving. If you're not moving very fast, you wouldn't necessarily expect to have a tremendous amount of momentum. So because it's based on these two things, the good news is that momentum is actually calculated fairly simply. And it's just momentum is mass times velocity. Lowercase p is used to represent momentum. I'm not entirely sure why, but m is mass and v is velocity. So if you know the mass and you know the velocity of the object, you can certainly calculate its momentum. Mass is obviously measured in kilograms, velocity in meters per second. Therefore, when I multiply kilograms by meters per second, I wind up with the craziest unit of all for momentum, a kilogram meter per second. You're just multiplying kilograms by meters per second because it's mass times velocity. So if you have some mass, you have some velocity, you certainly have some kind of momentum. Now, this is one of the big things. It's important to realize that momentum is a vector quantity. You must have direction, and this is going to come into play a little bit later, a little bit with the concepts, much more so with the math. Anytime something changes direction, that's going to have an impact on the momentum. So for right now, just realize you have to have the direction. It's not enough to say it had 10 kilogram meters per second of momentum. You'd have to apply a direction, north, south, east, west, positive, negative, to the right, to the left, so on and so forth. So please just know that it is a vector quantity, much like force, velocity, things like that. So you have to have a direction for that. So just look at a few quick examples. If I have like a Mack truck and it's moving very fast, large mass, large velocity, when I multiply those two large values together, I will get a large momentum. So here I have a large momentum for this object. Now for a snail that has a low mass and it's not moving very fast, low velocity, when I multiply those two numbers together, they're both low, so I'll get a small momentum. And that's what most people kind of realize. A big truck moving very fast is going to have much more momentum than this snail that's very small and is moving very slow. But it's important to realize that you can have situations where a snail could have more momentum than a truck. So if we look at this case, let's say you have a huge cargo plane, very large mass, but let's say it's just kind of slowly moving down the runway. It's not taking off yet. It's got a small velocity. So large mass, small velocity will give us some kind of momentum. But you could also have a very small bullet that's fired, small mass, but a very large velocity. So a large mass multiplied by a small velocity, or a small mass multiplied by a large velocity could give us the same momentum. So it's important to realize that it's not just the size of the object, it's not just the speed of the object, it's the product of those two. So there are situations where this snail could have more momentum than this big truck. If the truck wasn't moving or was moving incredibly slow, like fraction of what the snail was moving, you could have situations where smaller objects have more momentum than the larger object. And here's a prime example. You could have an enormous building, a shopping mall, skyscrapers in New York City, incredibly large masses, but they have no velocity and therefore have no momentum because there's no mass in motion, so to say. So you can kind of see here that velocity has a big part on it. The mass does as well, but it's not just one or the other. It's the product, the multiplication, the combination of those two that's going to give us information about the momentum of these objects. The only other thing that we would need to understand before we start to look at this in more detail is what's known as impulse. And Isaac Newton, long time ago, sat down, kind of looked at momentum and thought to himself, well, if I have a ball that's at rest and then at some point in the future it's moving, there's only one way that could have happened. And he realizes that a force must have acted on that object. And it's not too big of a stretch of the imagination to realize that force must have acted over a certain amount of time. Okay, so this force that acted on this ball for some given amount of time, that's what he coined impulse, which again is just the force acting over a given period of time. Some impulse came along, and this object gained momentum as a result of that impulse. It's important to realize that that impulse is not just the force, it's the force acting over a certain amount of time. He then also took a look at his second law and realized that if F equals ma, and we know from kinematics that acceleration is just change in velocity over change in time, well, he could replace that a value with just delta v over delta t, the definition of acceleration. Now, he didn't like this time component in the denominator, so by multiplying both sides by time, he found this equation, F delta t equals m delta v, where F is force, t is time, m is mass, and delta v is the change in velocity. And this is what's known as the impulse momentum equation. Okay, he realized that m delta v is really just the change in momentum, and the force acting over a certain time is the impulse. So just to break this down a little bit further, this concept of impulse, which is just the force acting over a given amount of time, well, since momentum is mv, then F delta t equals a change in mv, because m delta v is the same as saying just a change in mv, so the impulse is equal to the change in momentum. And that's a big kind of conceptual vocabulary understanding here. Anytime you hear the word impulse, they simply mean a change in momentum. Just like work is a change in energy, impulse is a change in momentum. And it's a result of a force acting over a certain amount of time. And that's kind of what this equation says. If a force acts over a given amount of time, a mass will experience a change in velocity. And these two products are equal to one another, which is why this becomes helpful in analyzing motion. So to quickly just look at a conceptual example, just like from before, a ball is at rest, has no momentum, a force acts on it over time, also known as an impulse, and afterwards it clearly has some kind of momentum. It has the same mass, but now its velocity is some non-zero number, and it does have momentum. So it's important to realize that the change in momentum, also known as m delta v, is equal to that force that acts over a given amount of time. The big takeaways, if we want to take a look at this, would be that the momentum of an object is the mass times the velocity. You should realize that you have to have direction. It's a vector quantity. Understand that both of these properties will affect the momentum of an object, so you can't always say that one object will always have more momentum than another. Objects that are not moving have no momentum because they have no velocity. And an impulse is required to cause a change in momentum, and that impulse is equal to a force acting over a certain amount of time. And that will produce a change in that object's momentum, and this is known as the impulse momentum equation. You understand those on a basic level right now, you have enough information to be able to move forward, and we'll look at this in more detail mathematically.